Swayam Prabha. Digital India. Educated India.
Hi everyone. In the last lecture, we have discussed about semi-inner product spaces. Today we are going to discuss about inner product spaces and a few examples. Let us start with the definition of an inner product. A semi-inner product on X is said to be an inner product if semi-inner product of X with itself is 0 implies X equal to 0. We have seen that in a semi-inner product space there exist vectors X such that in a semi-inner product of X with itself is 0 but X is non-zero. The pair X with the inner product is called an inner product space. If the field is R, then it is called a real inner product space. If the field is a complex plane, then this is called a complex inner product space. Let us recall the Cauchy-Schwarz inequality. Cauchy-Schwarz, Bunyakovsky, in the inner product case, modulus of inner product X with Y square less than or equal to inner product of X with itself multiplied by inner product of Y with itself for every X, Y in X. Now it is easy to check that so let us call this as equation 1, inequality 1. Equality holds in 1 if and only if there exists a scalar lambda in F such that X equal to lambda Y. Here we have to use the fact that semi-inner product of X with X equal to 0 implies X equal to 0 in the inner product space. Okay. Now using this inner product we define a new function define norm x as inner product of x with itself. So we show that this is a norm. So claim that this is a norm. You can quickly recall the axioms of norm. Let X be a vector space over the field F if there exists a function which we denote by this notation, which takes elements of x into R such that the following axioms are satisfied. The function value is always positive for every x in X. Second condition is the function value equal to 0 implies x equal to 0. The third condition is function value at lambda x equals to mod lambda function value at x for every x in X for every lambda in the field. And the fourth condition is about the function value at x plus y is less than or equals to function value at x plus function value at y for every xy in X. If there exists such a function, then this function is called a norm on X, and X with this function norm is called a normed space or a non-linear space. Again, if the field is F equal to R, then the space is called a real non-linear space. If the field is the complex plane, then is called a complex nonlinear space. Let us look at a simple example. Let us take x to be the complex plane, and in this case f equal to c. So define norm of z equal to mod z for every z in C or x. We can easily show that this function z going to modulus of z satisfies all the conditions of norm, and we also know that modulus of z is nothing but distance of the vector z from 0 to z. Okay. Now if you look at this example, let us actually get a nice geometric interpretation of triangle inequality, or the axiom that we have stated here. This is known as the triangle inequality. We will see now why this is called triangle inequality. And if you look at the first axiom here in the definition of norm, it says that the function norm takes only positive values. So that is very natural to expect, because as we told in the first example that it is nothing but the distance function when we define norm z equal to modulus z, and this takes positive value. And the third and fourth says that how this new function behave with the existing linear space structure. Okay. This norm also is a generalization of the length concept. So the second axiom also very natural to expect. If length of the vector is 0, then the vector must be 0. Okay, let us come back to the triangle inequality. If you take two vectors z and w, let us look at z plus w. So this is z plus w. Okay, so this length is norm z plus w or mod z plus w. This is mod norm w. This is norm z. Now the triangle inequality says that if you look at this particular triangle, the length of z plus w cannot exceed sum of length of z and length of w. This is the triangle inequality. For this reason, the fourth axiom in the definition of norm we call as a triangle inequality. Okay, let us look at one more simple example. Take x equal to r2 and f equal to r. For x equal to x1 comma x2 in x, define a new function like this as maximum of mod x1 comma mod x2. It is easy to verify that this new function defines a norm on x. Now our aim is to show that we can define a function, one variable function here, norm x equal to inner product x with x and square root of that. So, though we have not proved that this is a norm, but since we are going to prove it very soon, we can call this as a norm. So let us look at that part. So let be an inner product space. If you define this function, then this is a norm. on x, which is known as norm induced by the inner product. We will see that now. That means we have to show that, let us call this as star. The function defined in star actually satisfies all the axioms of norm. If you look at the definition, it is easy to look at if function value at x equal to 0, that means inner product x with x equal to 0, that automatically gives that x equal to 0, and it always takes positive values. And if you look at function value at lambda x, then we can easily show that that is mod lambda and multiplied by the function value. So only thing we have to show is that the triangle inequality, and in fact in most of the cases showing the triangle inequality is difficult, and other axioms are bit easy. Okay, so let us consider let us take let us consider square of this function. So this is nothing but inner product of x plus y with x plus y, and this is nothing but inner product of x with itself plus inner product of x with y plus inner product of y with x plus inner product of y with y. So this is nothing but, by definition, this is norm x square plus inner product x with y plus inner product x with y bar when we look at the complex plane, when we take the complex field. This is norm y square. Otherwise it is we don't have to do this in the real field. So this is nothing but norm x square plus 2 real part of this complex number inner product x with y plus norm y square. Now real part of any complex number is less than or equal to modulus of the complex number. We use that fact. This is norm x square plus 2 times mod inner product x with y plus norm y square. This is nothing but norm x square plus 2 times, this is less than or equal to inner product x with x square root inner product y with y square root plus y square. So here we use the Cauchy-Schwarz. Because modulus of inner product x with y less than or equal to inner product of x with itself square root multiplied by inner product of y with y square root of that. So this is nothing but norm x square plus 2 times norm x norm y plus norm y square. Again this is equal to norm x plus y whole square. Hence we can conclude that norm of x plus y less than or equal to norm x plus norm y, because we have shown that norm x plus y whole square less than or equal to norm x plus norm y whole square. Now taking the square root, we can get that norm x plus y less than or equal to norm x plus norm y. So this is the norm which comes from the inner product, which we call as the norm induced by the inner product. Okay, now there are a few important consequences of this one. Let us look at those things. Okay, the first one is that let us take a sequence x1 in the inner product space X such that xn converges to x. So here when we say xn converges to x in the inner product space, that means xn converges to x in the norm, in the induced norm. That means norm xn minus x goes to 0 as n tends to infinity, when this norm is the induced norm. Okay. Now using this we can show that the inner product is continuous in both variables. So let us take another sequence yn converges to y in x with respect to the norm. Then we can look at the Cauchy-Schwarz inequality, norm xn minus x yn minus y. So this is less than or equal to norm xn minus x multiplied by norm yn minus y. So this is another form of Cauchy-Schwarz inequality we have used, that is modulus of inner product x with y is less than or equal to norm x multiplied by norm y for every x, y in x. This follows from the Cauchy-Schwarz inequality and the definition of the norm that we have given. Now because of this we can say that this goes to 0 as n tends to infinity. That means we can conclude that the inner product is continuous in both the variables. Okay, let us look at a few examples of inner products and the norms which are coming from the inner products. The first example is r power n. Let us take x to be r power n and the field is R. Let us take x equal to x1, x2, so on xn, and y equals to y1, y2, so on yn in x. Define this two variable function as summation j equal to 1 to n xj yj. We know that this is the dot product or scalar product of x with y. It can be easily shown that this is an inner product on r power n. The induced norm here it is given by summation j equal to 1 to n mod xj square whole power 1 by 2. This is a Euclidean distance from the origin to x. So this is the norm inner product, and this is the induced norm. The second natural example is the unitary space x equal to c power n and the field is C. Let us take z dash, z1, z2, so on zn, and w as w1, w2, so on wn, which belongs to x. So define inner product like this: j equal to 1 to n zj wj bar. It can be easily shown that this is an inner product on C power n. The induced norm is, again, this is called the Euclidean norm or 2th norm of Z. It is given by summation j equal to 1 to n mod zj square whole power 1 by 2. So this is the inner product. And this is the induced norm. These are the two natural examples that we are already familiar with. One of the earlier examples, namely the polynomial space. You look at x as let us take x to be here a, b are real numbers with a less than b. Now let us take two polynomials. Let p of t as summation j equal to 0 to n aj tj, and q of t as summation j is equal to 0 to n some bj t power j, where aj are from c, j equal to 0, 1, 2, so on n, and bj's are coming from c and j equal to 0, 1, 2, so on. Now define inner product like this: j equal to 0 to n inner aj bj bar, and we can easily show that this gives an inner product on the polynomial space, and the induced norm is summation j equal to 0 to n mod aj square root of that. Okay, let us look at one more example, which is a space bigger than this one. Let us look at set of all continuous functions. Okay, let us take a, b to real numbers with a less than b. Let us take, and you take x to be CAB. That is set of all continuous functions taking values in C. F is continuous on AB. We know that this is a vector space with pointwise addition and scalar multiplication. If you take alpha to be a complex number, alpha times f at t is alpha into f of t. Now let us take two functions fg in x. Define inner product of f with g as integral a to b f of t g of t bar dt. Then we can easily show that this is an inner product on x, and the induced norm, this is also denoted by 2th norm integral a to b mod f of t square dt whole power 1 by 2. Okay, this is also example of inner product space. Let us further look at examples. Let us take X to be a vector space over C with a basis E1, E2, so on En. So if X and Y are in X, then we can write as X as summation lambda j Ej, j equal to 1 to n, y equal to summation j equal to 1 to n mu j Ej, where this lambda j's and mu j's are complex numbers from j equal to 1 to n. They depend on the vectors x and y respectively. So define this function as summation j equal to 1 to n lambda j mu j bar. You can show that this is also an inner product on X. And the induced norm, here also we denote this by norm suffix 2. This is nothing but summation j equal to 1 to n mod lambda j square 1 by 2. In fact, this example is also generalization of the Euclidean space C power n. So this is induced norm, this is inner product. Okay, yeah, let us look at one more example. Let us take X to be the C00 space, which consists of all complex sequences xn such that xn in C and xn equal to 0 for except finitely many n's. In other words, set of all sequences xn so that xn is in C for all n in n, and there exists some k in n such that xn is 0 for all n bigger than or equal to k. In fact, this k depends on the sequence xn. Okay, so if you take two sequences x and y, let us take x as xn and y as yn coming from x. Define inner product of x with y as summation j equal to 1 to infinity xj yj bar. The series on the right hand side of this equation is convergent because in each sequence there are only finitely many terms are non-zero, remaining are 0. So on the right hand side, that is finite sum. Okay, we can easily check that this is an inner product on C00 space, and the induced norm, again this is denoted by suffix 2. This is nothing but summation j equal to 1 to infinity mod xj square power 1 by 2. This is also generalization of the Euclidean norm. Okay, let us look at one more important example, the space L2. let us take x as L2 of n. This is by definition set of all sequences xn such that xn is coming from C for all n in n, and summation n equal to 1 to infinity mod xn square is convergent. That means this is finite. So for x equal to xn and y equal to yn coming from x, define a two variable function like this, summation j equal to 1 to infinity xj yj bar. So let us call this by equation 1, and first of all we have to show that the series is convergent, then only we can define the inner product. The inner product x with y makes sense. So the claim is that summation j equal to 1 to infinity xj yj bar is convergent. To prove this result, we need the Cauchy-Squarz-Bunyakovsky inequality. So instead of showing it is convergent, in fact we show more than that, that is the series is absolutely convergent. To show the series is absolutely convergent, we have to look at the nth partial sums of summation j equal to 1 to infinity mod xj yj bar, and then show that is convergent. So let us take consider summation j equal to 1 to n mod xj yj bar. So this is nothing but summation j equal to 1 to n mod xj mod yj. Now here we use the fact that whenever we have a sequence, whenever we have two real numbers a and b are positive, then we know that a minus b square is positive. From this we can say that 2ab is less than or equal to a square plus b square. That means ab is less than or equal to a square plus b square by 2. So here you take a as mod xj and b as mod yj, both are positive numbers. Now we can apply this result. So this is nothing but this is less than or equal to summation j equal to 1 to n mod xj square plus mod yj square divided by 2. So this is less than or equal to 1 by 2 of summation j equal to 1 to infinity mod xj square plus summation j equal to 1 to infinity mod yj square. We know that x is coming from L to n and y is also coming from L to n. So these two quantities are finite. So we can actually say that this is finite. Now on the left hand side we have a nth partial sum sequence of positive numbers which is bounded above, and that is also increasing. Hence we can say that the nth partial sum sequence is convergent. Hence the original series is absolutely convergent. So therefore is convergent, not convergent, absolutely convergent. Okay, what we have shown is we have proved that if we define a two variable function as in equation 1, the right hand side series is absolutely convergent. Hence this is meaningful. Now we can easily show that this function satisfies all the axioms of the inner product. Hence we can say that L2n with this inner product is an inner product space, and the induced norm in this case is, so you check that this is an inner product. The induced norm is given by norm x suffix 2, this is summation j equal to 1 to infinity mod xj square power 1 by 2. So this norm we call as a L2 norm, and the inner product also we can say that L2 inner product. So far we have discussed about inner product space and a few examples of inner product spaces. In the next class we will be discussing about two questions. Question 1: if we have a semi-inner product, on a space X, how to get an inner product from it. This is the first question. The second question that we are going to answer is that, suppose we have a nonlinear space, that means there is a norm on a vector space. Now, is it possible to find an inner product which induces the given norm? If X is a normal space, how to find an inner product on X such that this inner product induces the norm. So we will be discussing these two questions in the next coming classes. Thank you.